Good afternoon, everybody. Welcome and for joining us at the Agriculture Conservation Planning Framework Toolbox Lunch and Learn webinar series. We continue our series with August Froelich of the Nature Conservancy. And today we will be talking about water control structures and how the tool models water control structures. So I'll turn it over to August and he'll take it away.
Thank you, Jess. Give me a second here to share my screen. All right, how are we doing there? See what's going on?
Yep.
All right, as Jess said, I'm August Froelich. I'm a GIS analyst with the Nature Conservancy in Ohio, and I thought this was a good picture to start off with because this is one of the main reasons why I got started in ag nutrient issues. This is the Maumee River, the falls at Roche-le-Boeuf, a beautiful spot and a good reminder of where all of everything flows downstream. So I'm going to just talk for a second about the Agricultural Conservation Planning Framework Toolbox. It's a set of tools built on the Esri platform using either ArcGIS or ArcGIS Pro or ArcGIS Desktop with the spatial analyst extension. It also involves using a set of Python scripting tools and a set of tools in software called Tau DEM developed by Utah State. Now, the work for all of the development of this was done through the USDA Agricultural Research Service and was done in conjunction with the Natural Resource Conservation Service. A lot of what this tool tries to accomplish is identify which fields are appropriate for various conservation practices that have been identified by the folks who developed the tool and the NRCS, so that we can do a little bit more structured evaluation of the landscape to find locations for practices. And the practices basically fall into three groups. They're in-field practices, what I'm calling below field practices, and the sort of along field practices. Now, these practices are designed to treat tile drainage or surface runoff. As an example, for an below field surface runoff practice, we will talk about water and sediment control basins, or WASCOBs. A infield tile drainage practice is what we're going to talk about today, which is drainage water management. Now, the way that the tool has been developed in conjunction with the practices as they're described in the conservation technical guidance, what we see identified by the ACPF Toolbox are the practices that very closely emulate what the guidance considers to be an optimal location. So, for example, today we're going to talk about drainage water management, and that is basically mainly supported by Conservation Practice 554 through the NRCS. But all the rest of the practices that are identified for a Huck 12 watershed have, specific practices that they were targeted for, but also the toolbox sort of ignores or assumes that the entire watershed, there will be this implementation of these practices will take place in a context of whole watershed planning, as well as whole farm scale for our soil health and farm scale planning efforts. So this is a way to accomplish some of the goals and objectives that are set either at the farm site or at the watershed scale. Drainage water management is a little different than some of the ones that we've talked about previously, in that it primarily takes place underground, and it is sort of an actively managed practice. If you are at all familiar with how drainage tile systems work, generally they collect water underground, route it downhill until it outlets into a drainage way, ditch, or other collection system. What a water control structure will help do is allow us to manage the level of the water upstream of the control structure so that we can manipulate the amount of water in the soil at various times of the year. These the water control structures are reasonably priced. They're not terribly expensive. They're fairly easy to install, and they're reasonably easy to operate. We talk here about these adjustable riser boards, which are basically the dam that helps stop up the water, and you can add or remove levels to it to achieve the appropriate water table. And these can be installed in existing drainage systems, or could be added when a tile drain system is redesigned or upgraded or improved. So it's a pretty flexible piece of infrastructure that can help, as we'll see, accomplish several goals. So the main point of the way that this works is that we don't necessarily need to have the water table drained all year round. In Ohio, in the winter, we can keep the water table higher. And there's a lot of benefits to that, in that it helps maintain organic matter in the subsoil. It helps with nutrient processing, possibly in the soil, and can help a lot with general soil health. But that can also make it complicated to work the soil when it comes time to do operations in the field. So we can keep the water table higher throughout the off season in the winter, and then shortly before planting or other field operations, planting or harvesting, we can remove the impediments to the flow and allow the drainage tiles to achieve the base flow, and the water table will be as high as the drain tile. But then once field practices are primarily finished, we can add some impediment back and raise the water table, maybe not the entire height, but some height, and possibly improve access to water for the crops in the field. And this right here, that step has been shown through research to have significant yield benefits. The plants can have access to greater water and they perform better. So there's a direct benefit to this process. But additionally, one side benefit, or possibly the main benefit, depending on how you're looking at it, is that you can use these as a protection when you're applying liquid manure to a field. If you're applying to a field that is drier and has cracks or megapores in it, then the manure might run straight down into the tile and out into the drainage. Well, if you've got the stops raised when it's normally low, then you've got a lot of capacity to store that and hopefully process it in the tile drains, in the water that it's being held, that is being held by the in the drain tiles. So, oh, excuse me. As we've said in other presentations, this agricultural conservation planning framework toolbox uses a set of standardized, readily available public data, including LIDAR, soils, land cover, and then some ancillary data that varies depending on where you're at, such as roads and streams. And the one first step, the big hurdle that using the tool requires you to get over is what we refer to as hydroconditioning. The hydroconditioning just allows you to model the way water moves across the landscape. It helps you identify locations where water might flow, where concentrated flow exists. It can identify places where water doesn't flow as well in swales or ditches. And it can also identify places that water actually may not flow at all, such as depressions or wetlands or ponds. So doing this is complicated and tedious, but afterwards, you have a very effective means of representing the way water flows across the landscape. So drainage water management results aren't really apparent, and they're sort of constrained by the landscape. And I've been trying to use the same watershed across all these discussions. So we're in luck that we actually had one identified here. One of the main attributes of the drainage water management results are that the first screen is that the fields will have less than 2% slope, and that they will be of a certain size or percentage of a field. So that in this case, I believe it was greater than 20 acres of result. The tool also acknowledges that there are field boundaries that may or may not constrain ownership. For example, tiles are generally by field, but they may not be. And the tool can only tell that it assumes that if a field is flat, for a certain definition of flat, it is tiled. And by evaluating the amount of slope, the type of soil, and the area within a field, the tool will establish a polygon or a shape that describes the area that would be suitable for drainage water management. So basically, what we're looking at here is the area that would be inundated, let's say, by a water control structure if it were placed in the suitable location. So there's a lot to that, what I just said, and I'll go back to this hydroconditioning, where we start with the one field that the arrow is pointing at here. You can sort of make this out, right? Right here. Looking at it, you may not be able to tell that there's anything different from this field over here or this field down here. But because the power of GIS is used in this process, you are able to discern things that may not be readily apparent. So one thing I've talked about is the elevation. So the elevation is shown here, just with colors to demonstrate that, you know, the lower part of the elevation is down here where the stream flows off the screen. The higher part is right here. And you'll notice that there's a patch here that's all relatively similar colored. And consistently colored, which we'll see is generally an indication that there's a flatter area here where you get a constant color across a specific area. So using GIS, we can calculate the amount of the value of the slope for every 30-meter pixel. So if for every quarter acre, we can have an estimate of the amount of slope continuously across the landscape. So in this one, there's that large patch of consistently colored land again, probably the second largest after this floodplain down here. There's some redder areas that are stream banks and other types of sloping land, some human constructed, other natural. But one of the things that the toolbox does, in addition to calculating this continuous slope estimation, is that it will then do a calculation of the mean value of slope. It takes it calculates several different values of it, but this I'm showing you here is the mean value of the slope for each of these individual fields. So again, that large, consistently colored patch of land is identified as one field with not very much slope at all. There's a couple different ones that are similar. They're smaller. You may not be able to tell. There's a line right here separating these two fields, and each of these fields is evaluated individually. Some of these fields have higher slope, and higher being, in this instance, here, 4% slope, mostly driven by the existence of these stream reaches. But this is an example of the ancillary data that is used as an input, but we don't generally talk much about. So after considering the suitability of a location for a practice, the tool then describes the area of land that is best suited based on the conditions we give it. So we told the tool that we would like it to consider a certain amount of area that is to be the cutoff. So we'll say 20 acres at least, or some certain percent of the field that should be considered, which, let's say 50%, I think was the cutoff. And then we say vertically, consider a contour of 1 meter. And that would be the amount of land that would be controlled by one drainage control structure. So this is an iterative process, and there are some settings we can change in this where we could lower some thresholds or raise them, and the amount or the area covered by the results might change. But this area right here is, according to what we asked for, the area that would be involved in this practice. So it's a difficult thing to describe with the computer, except to say that this area would be practical. The next step would then have to be with having a drainage engineer or someone similar be able to look at this area and say, here, now that we know what might be effective, let's look at the drainage, let's look at the tile pattern, the way things are constructed now. Are we going to just improve what we've got, or do we want to move forward and try something completely new? So this is just the first step. But similarly, this is just one part, and this is, again, the power of the ACPF Toolbox, is that in addition to this drainage water management polygon that we've identified, the tool identifies a whole range of other practices, including the bioreactors, as we've talked about, the nutrient reduction wetlands previously, vegetative riparian buffers, grass waterways, and wascobs. So that's not just a practice by practice, field by field evaluation, but an entire watershed evaluation of each field and each field suitability for each practice. You can see there is just a patch of grass waterway identified as being overlapping the drainage water management polygon. So they aren't exclusive, and they can stack up to practices that achieve conservation across the entire HUC 12 watershed. Now this whole watershed approach is, I mean, I keep repeating myself here, but this is really the power of the ACPF Toolbox. That watershed that I've chosen to use in all of these as an example is one that I felt had a good representation of any of the practices that are identified, but drainage water management isn't well represented in this watershed, simply because I think this watershed has a little bit more topography than some of the other watersheds that we've been working in. Some watersheds in the Auglaize River watershed, for example, are much flatter, and as a result, there are many more fields that are suitable for drainage water management. More slope cuts down on the amount of area that's identified as suitable for management's water control structures. But nonetheless, even in this slightly more relief watershed, the tool identified 26 sites for a total of 725 acres, and each of them being approximately 28 acres in size. So 28 sites that each treat 26 sites that each treat 28 acres, I think is a pretty significant, could have a significant impact in reduction of, in particular, nitrates as they flow through the watershed aquatic system. But that's just one practice. There are several other practices that are involved and identified, and we know where they might go. There are caveats that, you know, the tool doesn't estimate cost or suitability of any particular place without knowing about existing easements, other ownership constraints, or even other drainage improvements. We don't know about the tile pattern, for example, for certain. We just know a field may be tiled. We don't know which way it goes or drains, etc. It's a complicated mess, and the tool just said, okay, let's look more closely. This place is suitable. I think that should wrap it up for us. The main point here is that drainage water management is one of the tools that is suitable for, and it's an infield practice for subsurface water that in conjunction with all of the other practices that the tool identifies will facilitate conservation. It gives you choices for where practices might be installed. It allows local staff for NRCS, for example, to work with landowners to identify locations that could qualify for any particular practice. It allows us to identify conservation opportunities at a watershed scale for things like non-point source plans, and it will efficiently allow us to identify places that would qualify so that we can hopefully find funding opportunities for installing those practices. So you can learn more about the ACPF Toolbox at acpfforwatersheds.org. There's a wealth of information there. We have videos and text and all sorts of maps that we can look at. Heartland GIS has helped us tremendously run these tools, and you can find them at their address there. And you can learn more about our ag program work at nature.org/Ohio. And I think agricultural work is right on the front page there. So Jess, I think that'll wrap it up for me.
Okay, thank you, August. Appreciate your time today and appreciate you running through the ACPF drainage water management section of the tool. I have posted in the chat the TNC Agriculture YouTube channel where we are going to post the recording of this Lunch and Learn series. In addition, you will be able to find the previous Lunch and Learn series for ACPF along with other videos and information that the TNC Agriculture team has put together. Join us again next month, the last Wednesday of the month, same time, for the next installment of ACPF. And August will, what are you going to go over the next month? What's our next series?
Bioreactors.
All right, bioreactors.
I don't know if that's true.
That
We will eventually talk about bioreactors. Though,
okay, well, we're continuing to run through the series and we'll cover all the practices. It's in the registration. I can't remember what it is right now. Okay, thanks everyone. Really enjoyed your time today.